Good day. Today we're going to discuss the vectors in two space, three space, and n space. So this is actually part of the concept of Euclidean vector space. Okay. So linear algebra is concerned with two kinds of mathematical objects, which are the matrices and vectors. Now, in we are already familiar with the basic ideas about matrices. So, in this discussion, we will introduce some of the basic ideas about vectors. And then, as we progress through this discussion, we will see that vectors and matrices are closely related and that much of linear algebra is concerned with that relationship. Okay, so let's start with the concept of geometric vectors. Now, engineers and physicists represent vectors in two dimensions, which is called two space, or in three dimensions, which is also called three space. Okay, and it is represented by arrows. The direction of the arrowhead uh, specifies the direction of the vector, and the length of the arrow specifies the magnitude. Mathematicians call these geometric vectors. So the tail of the arrow is called the initial point. Okay, so this is the initial point, and of course, the tip of the vector, the arrow, is the what we call as the terminal point. So in this discussion, we will denote that vectors in boldface. Okay, such the vectors should be uh, boldface, and we will denote scalars in lowercase italic type. Okay, when we want to indicate that a vector has initial point A and terminal point B, then we're going to write something like this. Okay, and vectors with the same length and direction, okay, are said to be equivalent. So something like this, they have the same length and the same direction. Since we want vector to be determined solely by its length and direction, equivalent vectors are regarded to be the same vector even though they may be in different position. So equivalent vectors are uh, also said to be equal, which we indicate by writing this one. So vector A is equal to vector W. Okay. So the vector whose initial and terminal points coincide has length 0. We call this zero vector and denoted by 0. The zero vector has no natural direction, so we will agree that it can be assigned any direction that is convenient for the problem at hand. Okay, so let's have the vector addition. There are numbers of important algebraic operations on vectors, so all of which have their own origin in laws of physics. So uh, we have this one, the parallelogram. Okay, parallelogram and triangle rule of vector addition. So for the parallelogram rule, if vector v and w, okay, are in two space or three space, are positioned so their initial points coincide, then the two vectors form adjacent sides of a parallelogram, and the sum, vector v plus vector w is the vector represented by the arrow from the common initial point of the vector v and vector w to the opposite vertex of the parallelogram. So this one. So this is the parallelogram rule. So you have uh, the A, okay, the figure A. So you have here the initial, okay, of the vector v and the initial of vector w. Okay, and then you have now the vector v plus vector w. Now there is another way to form the sum of two vectors. The second one is the what we call as the triangle rule for vector addition. So here, if a vector v and vector w are vectors in two space or in three space that are positioned so that the initial point of the vector w, okay, vector w is at the terminal point of vector v. So in this case, we are just going to place the uh, vector w at the top of vector v. Then the sum, the vector v plus vector w, is represented by the arrow from the initial point of v to the terminal point of w. So this one. Okay. So here we have a vector v, and then for the vector w, where the initial point of the vector w is placed on the terminal side or terminal point of vector v. Okay, and then connecting the initial of v to the terminal of w, then you have the sum of vector v plus vector w. Okay, now on the third figure, the C here, we can constructed the sum of uh, v plus w and w plus v by triangle rule. So this construction makes it evident that v plus w is equal to w plus v, and the sum obtained by the triangle rule is the same as the sum obtained by the parallelogram rule. Okay, so we can view the process of translating points. Okay, so here we have vector addition viewed as translation. So if v, w, and v plus w are positioned so that their initial points coincide, then the terminal points can be viewed in two ways. Okay, the first one is the terminal point of v plus w is the point that results when the terminal point of each translated in the direction, okay, uh, the direction of w. Okay, let me start. If the terminal point of v plus w, okay, is the point that results from the of terminal point of v. This must be terminal point of vector v. Okay, this is terminal point of vector v. Okay, is translated in the direction, okay, of uh, w. Okay, by the distance equal to the length of w. So here. So in other words, we are just translating the w, okay, from here. We translate it there. Okay. And then the second, the terminal point of v plus w is the point that results when the uh, terminal point of w, here, this is w, okay, of the translated in the direction of v, it should be v, uh, by a distance equal to the distance of v. So in other words, the v here, the vector v here, is just translated going there. Okay, so we can also view the vector addition that way. Okay, vector subtraction. In ordinary arithmetic, we can write a minus b as a plus the negative of b, which expresses subtraction in terms of addition. There is an analogous idea in vector arithmetic. Okay, so in vector subtraction, the negative of a vector v, denoted by negative v, is the vector that has the same length of v, but it is oppositely directed. So something like this. So take note, in figure A, this is vector v. So to illustrate negative v, then it has the same magnitude but opposite direction. And then you have the negative of v. Okay. The difference of v and w, which is denoted by w minus v, is taken to be the sum of this one. So you have a w minus v is equal to w plus the negative of v. Okay. So in this case, if you have the w, and then you are just going to have the, if this is the v, okay, and the opposite of v is this one. Okay. And then okay, the this one is your w minus v. So the difference of v from w can be obtained geometrically by the parallelogram method as shown in this figure, or more directly by positioning the w and b so their initial points coincide and drawing the vector from the terminal point of v to the terminal point of w, which is this one. Okay. Next, we have the scalar multiplication. Sometimes there is a need to change the length of the vector or change the length and reverse its direction. This is accomplished by a type of multiplication in which the vectors are multiplied by scalars. As an example, the product of 2v denotes that the vector that has the same direction as v but twice the length. And the product of negative 2v denotes that the vector that is oppositely directed to v and has twice the length. So we have this general result. If v is a non-zero vector in 2 space or 3 space, and if k is a non-zero scalar, then we define the scalar product of v by k to be the vector whose length is the absolute value of k times the length of uh, v, the length of v. The length of, it should be v here, the length of v, and whose direction is the same as of v if k is a positive and opposite to that of v if k is negative. So if k is equal to 0 or v is equal to 0, then we define kv to be 0. Okay. So in what to call this one? In the figure, as you can see in the figure, it shows the geometric relationship between the the vector v and some of its scalar multiples. So in particular, observe that when we are having negative 1v, okay, so this one, it has the same length of v but opposite directed or oppositely directed. Okay, so let's have parallel and collinear vectors. So suppose that v and w are vectors in two space or three space with a common initial point. Uh, if one of the vectors is a scalar multiple of the other, then the vector lie on the common line. So it is reasonable to say that they are collinear. However, if we translate one of the vectors, then the vectors are parallel but no longer collinear. So this creates a linguistic problem because translating a vector does not change it. The only way to resolve this problem is to agree that the terms parallel and collinear mean the same thing when applied to vectors. So although the vector 0 has no clearly defined direction, we will regard it to be parallel to all vectors when convenient. Okay. So let's have the sum of three or more vectors. Okay, so vector additions satisfies the associative law of addition, meaning the when we add three vectors, let's say u, v, and w, it will not matter which two vectors will we add first. So in other words, you could have uh, u plus v plus w, which is equal to u plus v plus w. Okay. So it follows from this that there is no ambiguity in the expression u plus v plus w because the same result is obtained no matter how the vector is grouped. In a simple way to construct the u plus v plus w, it is place the vectors tip to tail in succession and then draw the vectors from the initial point of u to the terminal point of w, which is this one. Okay. The tip to tail method also works for four or more vectors, just like this one. Okay. The tip to tail method also makes it evident that if u, v, and w are vectors in tree space with a common initial point, then the u plus v plus w is the diagonal of the parallelopipe that has three vectors as adjacent side, just like this illustration, the figure C. Okay, so we have vectors in coordinate systems. So up until now, we have discussed vectors without reference to the coordinate system. However, as we will soon see, computations with vectors are much simpler to perform if the coordinate system is present to work with. So we have the component forms of the zero vectors. Of course, if you have zero vector, then you have zero zero into space. And if it is in the three space, the component of 0 vector would be 0, 0, 0. Okay, so if a vector v in 2 space or 3 space is positioned with its initial point at the origin of the rectangular coordinate system, then the vector is completely determined by the coordinates of its terminal point. So we call these coordinates as the components of v relative to the coordinate system. We will write v, okay, as ordered pair to denote that the vector v is in 2 space with components v sub 1, v sub 2. And we could have v equals v sub 1, v sub 2, v sub 3 to denote that the vector v is in 3 space with the components v sub 1, v sub 2, and v sub 3. So it should be evident geometrically that two vectors in space or 3 space are equivalent if and only if they have the same terminal point when their initial points are at the origin. Algebraically, this means that two vectors are equivalent if and only if their corresponding components are equal. So, in other words, we could say that uh, V is equal to W if V is equal to, let's say, V sub 1, uh, V sub 2, V sub 3, and the W also is V sub 1, V sub 2, and V sub 3. Okay. It may be awkward that um, you have the ordered pair v sub 1, v sub 2 can represent either a vector with components v sub 1 and v sub 2 or the point with the components v sub 1, v sub 2. And similarly, for ordered triples. Both are valid geometric interpretation. So the appropriate choice will depend on the geometric viewpoint that we want to emphasize. Okay. Vectors whose initial points is not on the origin. So it is sometimes necessary to consider vectors whose initial points are not on the origin. So we have the vector p1, p2, okay, denotes that the vector, okay, with initial points p sub 1, which has the components of x sub 1, y sub 1, and the terminal point uh, p sub 2, x sub 2, x sub y, with the components of the vectors. Okay, given the formula that you have p sub, let's have uh, p sub 1, and then you have p sub 2, and this is vector, would be equal to, you have x sub 2 minus x sub 1, and you have y sub 2 minus y sub 1. That is the components of uh, vector p1, p2 are obtained by subtracting the coordinates of the initial point from the coordinates of the terminal point. So, of course, in this illustration, as you can see, okay, we expect that the components of the vectors, okay, has you have the p1, uh, x sub 1, y sub 1, and the p2 is x sub 2, y sub 2. Okay. So let's have operations on vectors in r raised to n. But let us first discuss the n space. So the idea of using ordered pairs and triples of real numbers to represent points in the two-dimensional space and three-dimensional space was well known in the 18th and 19th centuries. By the dawn of the 20th century, mathematicians and physicists were exploring the use of higher dimensional spaces in mathematics and physics. So today, even the layman is familiar with the notion of time and the fourth dimension, an idea used by Albert Einstein in developing the general theory of relativity. Relativity. Relativ- Relativity. Okay. Today, physicists working in the field of string theory commonly use the 11-dimensional space in the quest for the unified theory that will explain how the fundamental forces of nature work. Much of the remaining work in this discussion is concerned with extending the notion of the space to n dimensions. To explore these ideas further, we start with the terminology and notation. So, the set of all real numbers can be viewed geometrically by as a line. So, it is called real line, and it's denoted by r or r raised to 1. The superscript reinforces the intuitive idea that the line is one-dimensional. The set of all ordered pairs in real numbers, which is called two tuples, and the set of all ordered triples in the ordered number, which is called the three tuples, are denoted by r squared and r cubed, respectively. The superscript reinforces the idea that the ordered pairs correspond to points in the plane, which is the two-dimensional, and the ordered triples to points in space, which is the three-dimensional. So we have this definition. If n is a positive integer, then the ordered n tuples in the sequence of n real numbers, you have v sub 1 to v sub n. The set of all ordered n tuples is called n spaces or n space, and it is denoted by r raised to n. So you can think of the number in an n tuples v sub 1 to v sub n as either the coordinates of the generalized point or the components of generalized vector, depending on the geometric image you want to bring to mind. The choice makes no difference mathematically, since it is the algebraic properties of n tuples that are concerned. Okay, so let's have the operations of vectors in n raised to r raised to n. So our next goal is to define useful operations on the vectors of r raised to n. These operations will all be natural extensions of the familiar operations of vectors in two space and in three space. So we denote the vector v and r raised to n. Okay, using the notion that you have v is equal to v sub 1, v sub 2 to v sub n, and we will call 0 as 0, 0, 2, 0, 0, which is the 0 vector. So we noted earlier that the r squared and r cubed, the two vectors, are equivalent if and only if, okay, if their corresponding components are the same. Okay, so with that, we can have this definition. The vector v, with a component v sub 1 to v sub n, and vector w with the components sub 1 to wn are in r raised to n are said to be equivalent or so-called equal if you have the components are equal, and then we indicate writing that v is equal to w. Okay, so here our next objective is to define the operations of addition, subtractions, and scalar multiplications of vectors in r raised to n. So to motivate these ideas, we will consider how these operations can be performed on vectors in two space using components. Okay, so we have this uh, figure. Okay, and we should be able to deduce that in this case our v here is equal to uh, v1 v2, and our w would be w1 w2. Actually this one, this is our v and this is our w. So with that, our our uh, v plus w would be, you have v sub 1 plus w sub 1, and you have v sub 2 plus w sub 2, and our kv is equal to kv sub 1 plus uh, uh, kv sub 2. Okay, in particular we could have the uh, negative v. Okay, so you have negative v is equal to a negative 1 times v, which is equal to uh, you have negative v sub 1, negative v sub 2. And therefore, when we are saying that uh, w minus v, we could have w plus the negative of v, which is equal to you have the w1 minus v1 and w2 minus v2. So with that, these are our definition. Okay, so you have uh, our vector v has a component of v sub 1 to v sub n. Our vector w has the component of v sub w sub 1 to w sub n. Okay, these are the vectors of r raised to n. And if k is any scalar, then we could have, okay, we could have this definition. Okay, we have this definition that you have the uh, v sub let's write na lang. So if our vector v has a component of v sub 1, v sub 2 up to v sub n, and our uh, uh, vector w, okay, has the component of w1, w2 up to wn, which are all elements of r raised to n. And if this is k, if k is any scalar, then we could define that v plus w is equal to, you have v sub 1 plus v sub w sub 1, and then v sub 2 plus w sub 2, okay, and uh, v sub n plus w sub n rather. And then our uh, kv is equal to, you have k v sub 1, k v sub 2 up to uh, k v sub n. And our negative v is equal to negative v sub 1, negative v sub 2 up to negative v sub n. And our w minus v is equal to w plus the negative of v, which is equal to w1 minus v sub 1, uh, w sub 2 minus v sub 2 up to wn minus v sub n. Okay. So we have these, what we call this one, properties of vectors operations. So this is the theorem 3.1.1. So if u, v, and w are vectors in r raised to n, and if k and m are scalars, then you have u plus v is equal to v plus u. The quantity u plus v plus w is equal to u plus the quantity v plus w. The u plus 0 is equal to 0 plus u, which is equal to u. The u plus the negative of u is 0, and then the k times the quantity u plus v is equal to ku plus kv, and then the quantity k plus m times u is equal to ku plus mu, and the k times mu is equal to kmu, and the inverse of u is equal to u. Okay. So we have the following additional properties of vectors in n r raised to n, which can be deduced easily by expressing the vectors in terms of the components. So here you have the theorem 3.1.2. If v is a vector in r raised to n and k is scalar, then the uv, 0 times u is equal to 0, k times 0 is equal to 0, and the negative of negative 1 times v is equal to negative v. Okay. So let's have calculating without components. One of our powerful consequences in the theorem 1.1.1 and 3.1.2 is that they allow calculations to be performed without expressing the vectors in terms of components. So for example, suppose that you have x, a, and b are vectors in r raised to n, and we want to solve the vector equation x plus y equals b for the vector x without using components. So we will proceed as follows. So of course, the first, you have x plus a is equal to b, which is the given. So with this, we could have uh, x plus a plus negative a is equal to b plus negative a. Of course, this is add the negative. Okay, add the negative of uh, a to both sides. Okay, so with this, we could have that x, uh, the x plus a plus negative of a is equal to b minus a. So this is theorem 3.1.1, which is part B. And then you have x plus 0 is equal to b minus a, which is theorem 3.1.1 on part D. And then x is equal to b minus a, which is theorem 1.1.1 on part C. So while this method is obviously more cumbersome than computing the components in r raised to n, it will become important later in the discussion where we will encounter more general kinds of vectors. Okay, so line combinations. In addition, subtraction and scalar multiplication are frequently used in combination to form new vectors. For example, you have v sub 1, v sub 2, and v sub 3 are vectors in r raised to n. Then you could have uh, u is equal to 2v plus 3v plus v, and w is equal to 7v sub 1 minus 6 sub v 6v sub 2 and 8v sub 3, okay, which are formed uh, and in that way. Okay, so in general we will make a definition. So if w is a vector in r raised to n, where w is said to be the linear combination of the vectors v sub 1 to v sub r in r raised to n, it can be expressed in the form w is equal to k sub 1 v sub 1 plus k sub 2 v sub 2 plus so on up to k sub r v sub r. Okay, where um, the k sub 1, the k sub 2, and k sub 3 are scalars. These scalars are called coefficients of the linear combinations. And in the case where r is equal to 1, okay, this formula, okay, becomes w is equal to k sub 1 v sub 1. So that the linear combination of the linear or single vector is just a scalar multiple of that vector. Okay. So alternative notions of vectors. So up to now, we have been writing vectors in r raised to n using the notation of this one. Okay. So we call this comma delimited. Okay. So you have comma delimited. Okay, so you have comma delimited form. However, since the vector in r raised to n is just the list of its n components in the specific order, any notation that displays these components in the correct order is a valid way of representing the vector. So, for example, uh, these vectors, these vectors can be also written as this one, okay, which is called row matrix. So this is row matrix form. And this one is called column matrix. Okay. The choice of notion or notation is often a matter of ways or matter of taste or convenience. But sometimes the nature of the problem will suggest a preferred notions. So these notions, the three notions that is presented in this slide, will all be used in various places in our next discussion. Okay, so far we have discussed the geometric vector, the direction, the length, the initial point, the terminal point, the equivalent vectors, the zero vector, the vector addition in the parallelogram rule and triangle rule, and then we have the vector subtraction, the negative of vector, scalar multiplication. We have the collinear, which are parallel vectors, and then components of a vector, the coordinate of a point, the entropole, the n space, the vector operation in n space, which are the addition, subtraction, multiplication, scalar multiplication, and we also have the linear combination of vectors. So these concepts are then taking into considerations in performing geometric operations in vectors, algebraic operations on vectors, determining whether the two vectors are equivalent or collinear. We do also have sketch vectors whose initial and terminal points are given, and then we have finding the components of the vector whose initial and terminal points are given. So these are the concepts that we have discussed for this video. So thank you very much.